Right, I thought I'd go through this one, not because it's that bad actually, but on the surface of it, it sort of looks really complicated. So just to convince you that it's not really. So we've got two small smooth spheres, A and B, with equal radii. The mass of A is 2m, mass of B is 3m. The spheres are moving on a smooth horizontal plane when they collide. Immediately before the collision, the velocity of A is 5j. And the velocity of B is 3I minus j. Sorry, it should just be a 1 there. Immediately after collision, the velocity of A is 3I plus 2j. So A's coming off this way. And then we're kind of in this situation of going, oh, crikey, what's going on? So it looks like B might go off up here somewhere, but we don't really know. And then at that point you could get in a bit of a sort of muddle with it all, because the line of impact isn't parallel to either the vertical or horizontal axis. So unless that's stipulated, you can assume it won't be. But we're looking for the speed of B after the collision. And actually, we don't need to worry about all this. This was kind of the whole point of doing this one. So we can work with momentum as a whole. So you don't have to split this into your parallel perpendicular to line of centres. So we can do 3m, lots of 3, 1. So any signs are incorporated within these vectors. So plus 2m, lots of 0, 5. They just don't have. It just happens not to be any negatives. Equals 2m, lots of 3, 2. Plus 3mv. And then working that through, the m's all cancel off, so that's quite nice. 3v comes out as equaling so we've got 9 minus 6, which is 3i, and then I've got 3 plus 10 is 13 minus 4. Is that right? 3 plus 10 minus 4 is 9. Sorry, this is different to what I've got written down here, hence the pause. Why has that come out as being that? 3i. Oh, sorry, this is a minus j, that should be a minus 1 there. Which gives you a minus 1 there. So yeah, apologies, that was 3i minus j there, so I should have written that as 3 minus 1. So minus 3 plus 10 is 7, minus 4 is 3. And so from there, v is equal to 1, 1, and so the speed of b is equal to square root of 1 squared plus 1 squared, which is equal to root 2. And then for part B, we want a unit vector parallel to the line of centres. So again, that feels a little bit onerous, but we can use impulse for that. So we can look at the impulse that A receives. So the impulse is equal to the change in momentum. So it's momentum afterwards. So mv minus mu. So that's going to give me 2m lots of 3 minus 3. Which is, I can pull a 3 out of there, so that's equal to 6m 1 minus 1. So we want a unit vector in the direction of the impulse. So the direction of the impulse is 1 minus 1. And so a unit vector in direction of I is equal to 1 over root 2, 1 minus 1. So the impulse is acting along the line of centres and perpendicular to the line of centres. There's no change in the velocities of the ball.